Hi, and welcome back. Today's lecture is combining two sections. I have section 7.7, simplifying complex fractions, and section 9.2, where we are working with absolute value equations. So let's jump right in. If I'm dealing with a complex fraction, there are actually two methods that you can use to solve these types of problems. And a complex fraction is a fraction over a fraction. It sounds very complicated and it looks very scary. It looks like I have fractions within fractions, and it's like, I didn't like fractions to begin with. Why do I have more? It's actually super, super easy. Think about what a fraction is literally saying. If I talk about the very basic fraction, a over b, I am saying that I have a divided by b. This literally translates like so, a divide b. The fraction is just a simple way of writing this notation. So I'm going to take this same idea and I am going to apply it to this problem. What do I have? I have one fraction, which is 5x over x plus 2, divided by my denominator fraction, which is 10 over x minus 2. So I'm literally translating my complex rational expression, or my complex fraction, into two regular rational expressions. There's nothing complex about them, but I am dividing. Now, remember, how do you divide rational expressions? This is keep, change, flip. So keep, change, flip, very simple. You keep that first term. So I'm going to work vertically now. That first rational expression, you keep it. You change your sign from division to multiplication, and you flip your second rational expression. Now, at this point, since you are in multiplication, you would want to factor to see if there's anything that can cancel out. The x plus 2 and the x minus 2 cannot cancel, and they also cannot factor. There's no standalone x anywhere in this problem except for right here, so it cannot cancel. But 5 and 10 could simplify. So let's take that. So 5 cancels out there. 5 goes into 10 two times. Now going straight across, I have x times x minus 2 over 2 times x plus 2. And that is it. That is all there is to it. You could technically simplify this one step further, but just to go over the concept, I'm actually going to stop right there. So I am looking at having one fraction dividing by another fraction. I translated it as such. I then keep, change, and flip so that I have a multiplication problem. I factored out whatever I could cancel, I did, and everything that I have left came down to my solution. That's it. That's the whole process right there. So that being said, this is what we would term as essentially method 1. So you're looking at method 1 as on your notes. I'm going to just write up here a quick little note indicating this is method 1. Let's look at another problem. Sometimes these problems look really scary, such as this one. Whew, that looks terrifying, doesn't it? I have 4 fractions inside of one bigger fraction, and it's like fraction inception. And if you've never watched the movie Inception, you totally did not get that reference, and that is A-okay. But here's what we're going to do. There's a couple different methods, like I said. That was method 1, where you looked at one fraction dividing by another. Method 2 is slightly different. Now, as I'm looking at this particular problem for method 2 and reading the notes, it says multiply the numerator and denominator by the LCD of the fractions in the numerator and denominator. Huh? That sounds really scary and like what's happening? I don't know, right? It's super easy. It's saying look at all of your fractions within the problem. Look at each one of the denominators and identify what is the LCD of all of the denominators within the complex fraction. So the LCD of all four of these little fractions, make sure that looks like a y. There we go. So I have y squared, I have y, I have x squared, I have x. My LCD would be x squared, y squared for the whole thing, for everything in there. Great. Now we are going to multiply every single term here by the LCD. So x squared, y squared, x squared, y squared, x squared, y squared, x squared, y squared. This helps us because it cancels out some stuff. So here the y squared cancels. That's x squared times x is x cubed. Here a y cancels with y squared, leaving me 1 times x squared y. So that's plus x squared y. Here my x squareds cancel. I have y times y squared, which is y cubed, plus here x can cancel with one of these x squareds. So that leaves me 1 times xy squared, or xy squared. Ooh, that doesn't look as scary. You have a lot of working pieces still, but it doesn't look as scary. So here's what we're going to do. Looking at this particular problem, can I factor anything out? Well, it looks like this numerator has a GCF of x squared. When I take that out, I have x plus y. What about the denominator? Looks like they have both a y squared, so I'm going to pull that out. And I have y plus x. Huh. Now x plus y and y plus x, the signs are all the same. So these are actually the same exact thing. It's like if I had 1 plus 2 is 3 or 2 plus 1 is 3. It's the same exact thing. My signs are the same. I'm doing the same exact action here. So I can cancel these out. And I'm left with x squared over y squared. And this is what we would call method 2. Now, I want to point out, I'm going to stop here for just a moment. I want to point out the differences. Method 1 seems pretty intuitive, and it works great if you have one fraction dividing by another fraction. So it works absolutely great if you have this kind of situation. However, it doesn't work so great when you have multiple fractions in the numerator or multiple fractions in the denominator. So now you need something a little bit more robust, and that is the method 2 solution. The method 2, again, looking at the LCD of everything within that problem and multiplying everything within that problem by that LCD. That cancels out your fractions, and it leaves you with one simple rational expression. And you should look to see if you can factor it and cancel anything out. Simplify it. Okay, now let's take a look at another example. And I'm going to show you both methods with this next example. So I am going to erase all of this to get all my board space back. Method 1 and method 2 can really boil down to preference. Obviously, I showed you two great examples where each can be applied in its unique situation. But I'm going to show you an example where you can modify a little bit and really choose which method you like best. So, example number 3. I have x minus 4 over x squared minus 25. All of that divided by 1 plus 1 over x minus 5. Ooh, lots of stuff here, right? Let's look at this problem from the lens of method 1. The lens of method 1. So the first thing about method 1 is, do I have one fraction divided by another fraction? No, not presently, because I have 1 plus 1 over x minus 5. So how do I get this denominator to one single fraction? Well, 1 is something over itself, right? So that's technically like x minus 5 over x minus 5. So let's look at this problem if we were to write it as one single fraction. Here we go. So this would be like x minus 5 over x minus 5 for this one value, plus 1 over x minus 5. These are common denominators. Just looking at this big denominator right here, these are common, so I can combine those. So this technically would be like x minus 4 over x squared minus 25. Nothing's changed up here. Over, this would be like x minus 4 over the x minus 5. So I've modified from my original problem, which did not have one fraction over another fraction. I modified this problem so that I did have one fraction over another fraction. Awesome. This means in this situation, I can apply method number 1. At this point, I have x minus 4 over x squared minus 25 divided by x minus 4 over x minus 5. Now in this situation, keep, change, flip. I have x minus 4 over, I'm going to factor this at the same exact time just because I'm going to save a step. If you don't want to do that at this point, you don't have to. We're going to then multiply. This is x minus 5 over x minus 4. So that is keep, change, and flip. Keep, change, flip. I did factor my denominator here, the x squared minus 25 to x plus 5, x minus 5, because it is a difference of squares. After you factor, since you're in a multiplication problem, look to see if you can cancel anything. Indeed, I can. The x minus 4 cancels. The x minus 5 cancels. And I am left with 1 over x plus 5. So that is the method 1 process. So I'm going to write that over here. That was method 1. And I'm just going to put my big line here so that you can see method 2 below it. So same exact problem. One over x minus 5, just like so. So now I'm looking at the same exact problem from the lens of method 2. So the lens of method 2, I want to know what is my LCD of the entire set of problems. So I have an x squared minus 25 here, I have just 1, and I have x minus 5. So my LCD, thinking of this as a factored form, would be x plus 5, x minus 5. That's my LCD for the entire set of fractions that I have. I'm going to multiply that LCD by everything here. So x minus 5, x plus 5. Same thing here. And same thing here. Okay. Now, this cancels completely. That's great. So that leaves me x minus 4 in my numerator. That canceled completely for the denominator value there. Over here, nothing cancels, so I have x minus 5, x plus 5 still, plus, because I'm adding, my x minus 5 can cancel. I'm left with 1 times x plus 5, which is x plus 5. Great, now I can simplify even further. Let's see what I get. So the numerator of x minus 4 did not change. This is going to be x squared minus 25 plus x minus 5. I can do a little bit of work still here, so I'm going to. That's x minus 4 up there. This becomes x squared plus x, and then negative 25, and then minus 5 there. I am looking at, sorry, that's plus 5, x plus 5. I don't know why I wrote that incorrectly. I'm looking at it and saying, wait a minute. So negative 25 plus 5 is actually x squared plus x, and then that would be minus 20. This can factor out, so I'm going to factor it. I have x, 20 breaks up into 5 and 4. Signs are opposite, the greater is positive. And hey, look, I can cancel my x minus 4s. That's 1 over x plus 5. Same exact thing, either way. But here is a very good example of how you can use methods 1 and 2 on the same kind of problem. So very, very important stuff to look at. And honestly, it comes down to a matter of preference, whichever you prefer more, but you do need to know both methods. Okay, so that is it for section 7.7. I'm going to go ahead and continue into section 9.2 at this particular stage. And I got to get all my board space back because I took a lot of board space there. Okay, section 9.2, let's talk about some absolute value equations. So first and foremost, if I have the absolute value of something, then it always comes out to a positive value, right? Yeah. But it also means that you could have a negative value. So x could be positive or x could be negative. The end result of an absolute value is positive. But what this is actually saying is that x could be negative inside. Here's what I mean. Let's say I have the absolute value of 4. Absolute value of 4 is 4. What about the absolute value of a negative 4? Still 4. Interesting. So if I had the absolute value of x is equal to 4, I could say that x is either negative 4 or positive 4. And so absolute value can include the negative results within the x variable, or within whatever variable you happen to be using. Now, let's try this in practice. Let's say I have, get me some board space. Let's say I have the absolute value of x plus 2 is equal to 3. How do I solve this out? Well, I could say that x plus 2 equals 3, or x plus 2 is equal to negative 3. Why negative? Well, it's the same exact reason as why we said that x here could be a negative 4 or a positive 4. So we're just solving out, and we have to say that the absolute value could go in both directions. Now, solving, I get x is equal to 1, x is equal to a negative 5. Let's just check. If I plug 1 in, 1 plus 2 is 3. Absolute value of 3 is 3. That works. What if I put negative 5? Negative 5 plus 2 is negative 3. Absolute value of negative 3 is positive 3. So both of those are real solutions. So I can say that I have x is negative 5 or 1. Great. Let's try another one. Let's say I have the absolute value of 3x minus 4 plus 2 is equal to 11. Now, one thing to note about absolute value when you're working with equations, especially with multiple components within those equations, is that you really want to have the absolute value itself isolated as much as you can. So that means I'm going to move this 2 over. So I'm going to have absolute value of 3x minus 4 is equal to 9. At this point, I can split up. I have 3x minus 4 is equal to positive 9, or I have 3x minus 4 equals negative 9. Solve. So that gives me 3x is equal to 5. Oh, I'm sorry. I'm going crazy there. I have 3x is equal to 13. Excuse me. Divide by 3, x is equal to 13 thirds here. On this side, I have 3x is equal to a negative 5. That's where I got my 5 from. I was jumping around. Divide by 3, x is equal to a negative 5 thirds. So both of those are potential solutions. So x can be negative 5 thirds or 13 thirds. Awesome. Let's try one more. Absolute value is very easy to work with. Let's say I have the absolute value of 5x plus 2 is equal to a negative 7. What would I do here? I want you to notice something. The end result of any absolute value is positive, and oftentimes you hear the reference of absolute value is always positive. Well, that's pretty accurate. So what we're looking at here is the absolute value is equal to a negative. Ugh. Guess what, guys? No can do. This is no solution. Because you're not equaling to a positive value with the absolute. And there's nothing to change this value out here without having to drop the absolute value bars. So, no solution if your absolute value equals a negative. But as you're looking at absolute value equaling a positive value, as it does in this case and the other cases we've worked with, this is where you would split up and work to find the values of x that make the problem true. Okay, so guess what, guys? That is it for these two small sections. They're very finite, but that is all we have for right now. I have another lecture coming up in just a few minutes.